Is there any question? No? Okay. So we need to practice more examples on direct proof and then make it to the indirect proof and prove by contradiction. Okay. So for today, indirect proof is your main job, but we have one more practice problem on direct proof. Okay. So what was the direct proof? Your direct proof is you starting with the P, you end up with the Q. Okay. So direct proof means your statement is always the P then Q. So your statement is always P then Q. So when we say direct proof, you started with the P, you start with the P to be true. So you start with the P to be true, and then you prove it, you show it, the Q is true statement. The Q is true statement. So you start the P and you end up with the Q to be true. That's called the direct proof, okay? We did a few examples. Now we want to have I think one from the lecture note, and I'll add more, okay? So are we ready? What is in this statement? What is in this statement, the P or the hypothesis, and what is the Q or conclusion? What's the P? If, then. If what?
If n to the third plus n.
No, that's what you want to show. No, that's what you want to show. You want to show, you want to show NQ plus N is even number. You want to show NQ plus N is even number, okay? So what do we have as if, or what is the assumption?
For all an element of natural.
Yeah, so that's exactly, N is natural number. So if is N all natural number or one natural number or arbitrary natural number, so that's given, then you want to show NQ plus N is even. Okay, so this is a P statement, which we call it hypothesis. That's what you know. And this is the Q statement, and that is what you wish to show is true. You don't know it's true, but you wish to show that's true, okay? That is the conclusion. So, first of all, before writing the proof, any idea how we can show NQ plus N is going to be always even number? Do you guys have any idea why or how for any number NQ plus N can be even? No idea?
Think the n for one, okay, so n times the power of 3 plus n, which is 1, is equal to 2, the name becomes even.
Okay. So that's one example. But it doesn't show it's true for all numbers.
This is for
Okay. Okay, that's a good point. What's the difference between 1 and 2?
They're whole numbers that have
What is the difference between them?
well, this one.
1 is
Oh,
odd, 2 is even. So if it works for 1, probably works for 3, probably works for the 5, probably works for the any other odd numbers.
no, not all.
But can I just try to okay, so let's see. When we say all natural numbers, they are either even or odd. So that's just the only possibilities we have, right? So we have only even or odd. So then the way that you were thinking was correct. Actually, we were thinking about if it works for all even numbers, and it works for all odd numbers, so it's working for all of natural numbers, okay? So we want to make it two separate cases. So we want to exactly think in the same way, but we can't prove anything with examples, right? So we always prove things in general case. So if for 1, 2, 3, 10, 12 works, we don't know whether it works for infinity or 1,000 two medians, okay? So we can't never prove something with the example. We can think with we can just really find the process with the example. So as you told me is 1, and then it's 2. So that means you're looking for one to be odd, the other one to be even. So then I can think about, can I make the cases in general case for odd numbers, which looks like 2k plus 1, even numbers for 2k, and try whether it works or not, okay? So that's a good plan. So let's write it down. Do I have questions, guys? Okay, so as we know, we have to consider this is just the arbitrary number that you have, n to be in what is natural number, be any arbitrary number. That's just your first step. And then, as you said, we know n is either even or odd. There are not other cases, it's only two cases. So case number 1, you can consider if n is even. So then according to what we call definition for even numbers was 2 times k for some k to be for all of the cases that we defined, we consider k to be integers, okay? So, but since we are sure n is a positive number, is natural number, I don't want to risk, I'll just say k to be integer. Sorry, a k to be natural number, okay? So natural number does not have 0, it's 1, 2, 3, 4. So if I say k is in the z, it's risky. You might consider k is -1 or -1/2. No, it's not, okay? So k is only a positive number because n is only positive number. So then try to make n cube plus n. So that would be a 2k to the power of third plus a 2k. So that's a 8 cube plus 2k. And then you factor a 2 out. That works, right? This is okay. That's exactly what you want. You want to have a 2 times of something. So for even numbers, it seems always works. So you just say, since what is it? 2k cubed plus k is a natural number. So then n cubed plus n equals 2 times, I'm going to call something like always. So let's say this is a k1. Two times k1. So that would be for some k1 to be a natural number. So n cubed plus n is even. So, and you can do the same exactly thing for the odd numbers, okay? So case number 2, if n is odd, then n equals 2k plus 1 for some k to be natural, and then I'm copy paste, okay? So I'm just really replacing with the odd numbers this time. You're replacing n to be odd number, you're replacing n to be odd number, and then cube, what was it? 8 cube plus 12k squared plus, that's after simplification, okay? 6k plus 1 plus 2k plus 1. That's after simplification, which obviously I can factor it 2 out. So obviously you can factor it 2 out. 4k cube, 6k square. You have a 6k and 2k, so it's a 8k factorial 2 is a 4k left. You have a 1 and 1 is a 2, so 1 left. I'm okay with this one. So one more time, we highlight what we are doing. There are 2 cases for all natural numbers. Either could be even or odd. It could be either even or odd. For being even, so means 2 times of k. For being odd, means 2 times of k plus 1. For either cases, you could show if you have nq plus n, you're having twice of something, so it's even. If you have nq plus n is twice of something, so it's even. So you could show it's even no matter what. No matter it's even or odd, the nq plus n is even. Does it make sense? Any question here? Any question here? No? You agree? Everything is fine? So let's just continue with indirect proof. Okay, so let's just say what does the indirect proof say. So remember, when you were in logic, so again, first of all, what is the logic behind of the indirect proof? So when you were in logic chapter, we just learned P then Q is the same as Q naught then P naught. So we have a truth table, truth value table for all of these statements of P and Q, and we got a tautology. We knew these 2 statements are the same. So all of these theorems that you're trying to prove are if then statements. They are implication statements. If they are implication statements, so you can do it by contrapositive. So this is called contrapositive. This is called contrapositive statement, okay? So what does it mean? In order to just prove P then Q, you can directly start with the P and prove the Q. That's a direct proof. Not if you don't like it or if it doesn't work, so you have to go backward. So you have to say, I can't prove directly from P to the Q, but I can just say, if not Q, then not P. If not Q, then not P. So then I'm doing the same thing. So then I have the same equivalent problem, okay? So this is what you need to fill out over here. Contrapositive is Q naught, then P naught. So contrapositive is Q naught and P naught. That's what we call proof by contrapositive. Actually, we have one more proof, which is proof by contradiction, which is different, okay? So for now, we want to say, okay, if I can't directly go from P to Q, it's fine. I will go from not Q to not P because they are the same, okay? This is one statement that actually does not work with the direct proof. So why? This is your P statements and this is your Q. P statement says a square is just even number, and then your second statement or the Q or your conclusion or what you're supposed to show says n is also even. Okay, so we'll just make a scratchbook. We just think about. So what's going on? Your first statement says n squared is even. Okay, so your first statement says n squared equals 2k. So what do you think? What should be your next step if you want to show n is also even? What would be your next step if you want to get to the n to be also even? What do you think? Idea? No?
Just then by itself.
Yeah, you want n by itself. You might say, can I square both sides? So think about if you square both sides, what happens? So you'll have n here. That's perfect. That's what you're looking for. But that doesn't help me, right? That rad2 does not help you anymore because then it's just not showing is even or odd. It's just rad2. So it seems the direct proof doesn't work. Seems the direct proof doesn't help me. Okay, so let's make it the contrapositive to see how it helps. Okay, so this is going to be the backward. I have what? I have, first of all, the statements to be contrapositive. So this is contrapositive of this statement. Okay. What do I have? You should say what is not Q, then not P. Give me. What is not Q, then not P? No, read the statement and then rewrite.
Even.
N is not even.
Then n squared is not even.
Can I write odd instead of not even? Can I write odd instead of not even? Agree? So this is going to be, this was P statement, that was a Q statement. This is not Q statement, and this is not P statement. That's not P statement. And so the top one was P then Q, this one was Q naught, then P naught. Okay, let's see how, now you need to start with the Q naught, right? So that's now your brand new problem. So the contrapositive now is the brand new problem that you start with this not Q and then you prove not P, right? So now you're assuming your N be an arbitrary integer that you start with, and then you have N is odd. Can I write arbitrary odd integer? Odd integer, sorry. So then, according to what we call odd, definition is 2k plus 1 for some k integer. Then you have to square. You have to square because you're supposed to show n square is odd. So then you have 2k plus 1 to the power of second. So that's just the algebra. You square it. So this is this. You factor the 2 out. This is okay now? Is it n squared now odd or not? Did I show n squared is odd? Did I show the n squared can be written as 2 something plus 1? This is okay? So let's just say this is a maybe k sub 1. And then since k sub 1 is 2k squared plus 2k integer, so n squared is 2k sub 1 plus 1 for some k1. N squared is odd. And that's it, you stop. You couldn't prove the direct statement. You could not prove the direct statement. So, but you could prove the contrapositive. So therefore, the original implication also holds. Question? Since we are learning different methods of the proof, so I will say the main challenging is to decide which one works. That's the main challenge. Otherwise, the statements or the proofs are not really that much complicated that you have to write a page or 2 pages about it. So if you can decide whichever statement is true, you can, I mean, you can decide whichever method you want to use, you can start from the left side and get to the right side, okay? Question here? The third method, the other method of proving is proof by contradiction. So what's the proof by contradiction? What is the proof by contradiction? Okay, so your statement always is P then Q. So you are always saying if P is true, then Q must be true. Okay. Proof by contradiction, it's a little bit different. It says you consider the P is true, but Q is false. So you say P is true, but the Q is false. And then you do some steps and you get to the contradiction. So one, I will say silly example, okay? Let's say if I get an A, if you guys get an A, you pass 270A, okay? This is just the P then statement, okay? P then Q statement. So then what is this contradiction method says, you say P is true, means I got an A, or you got an A, okay? But Q is false, but you didn't pass the course. It's really silly, right? So it's nonsense. Nonsense, I call it contradiction, because this is really contradiction. I can't get A and not pass the course, okay? So that's what's happening for any of this statement. You consider your P is true, but the Q is false, and you say, no, this is nonsense, this is false. It doesn't work, it's a contradiction. So then you accept the Q was true from the beginning, okay? Is it okay now? Make sense? So for example, so this is the example. It says, I'm just reading here what I said exactly. So you suppose this statement is false. So you suppose the P then Q is false. So what does it mean? You consider the first one is true, the other one is false. So you consider P is true and then Q is false, and then you try to get something nonsense, something which is contradiction. And then you back to say, this is false. I mean, from the beginning, Q was true. Okay, you change your word, you just say, okay, I'm sorry, Q was true. I made a mistake, okay? Can we practice here? This is going to be the P statement. This is going to be the Q statement, okay? If you want to make this one to be false statement, you have to say P is true, but the Q is false, okay? So prove by contradiction. Prove by contradiction. Assume P is true. And Q is false. Agree? Assume your P statement, which that equality is true, but the Q is false. Q is false means X is not 7, okay? This is okay? Do you agree with this one? So let's see what's the contradiction, okay? Let's see what's the contradiction. I'll have, since you're having x cubed minus 7x plus 7x squared plus minus 7 equals 0. You make this grouping and then you factor 1x squared out. So you have x minus 7 plus x minus 7. So you factor the x minus 7 out. So you're having x squared plus 1 equals 0, okay? Since you just say x is not 7, then x minus 7 is not 0. X minus 7 is not 0, so then the product is 0, right? So then x squared plus 1 has to be 0. How can I make the 0? If the first one is not 0, the second one has to be 0. So then you have x squared equals -1, then you have x equals, which is no real solution, right? Which is no real solution. So that is not real solution. This is not real solution. That is a contradiction. That is a contradiction. This is a contradiction. Okay. So what's the conclusion? X was 7. So this statement that you switch it to be not Q makes all of this to be false. This assumption that you consider not Q was the only reason that you got the contradiction. You get something false, something nonsense. So then you change your word, say, sorry, X was 7. Okay. Any question here? Do you guys have any question about how the logic is behind this proof by contradiction? No? This is fine? So let's practice one more time. This is the P statement. This is the Q statement, okay? I want to prove again by contradiction. Sometimes it happens. Sometimes you could really prove it by direct proof. You could prove it by positive. You can prove it by contradiction, okay? Sometimes you have all of the 3 choices and all of them works nicely. So I'm practicing now the proof by contradiction. That's why I'm trying proof by contradiction here, okay? So you suppose your P statement is true, that this statement is true, and your Q statement is false. Q statement is false. Less than equal, so bigger than equal. So this is not Q. This is not Q. Okay. Do you remember in algebra, if the absolute value is bigger than rad5, is the same as saying x has to be bigger than equal. Actually, does it have equality? Yeah, equality. Yeah, bigger than rad5, or x has to be less than equals negative rad5. Do you remember this one? Let me just make the real line. So on the real line, if you're having negative rad5 and rad5, and then your absolute value is bigger than rad5, so you're right over here. You are either on the right side of rad5 or on left side of negative rad5, then the absolute value of your absolute value of x is bigger than rad5. This is fine, right? Algebraically, makes sense? So then I'll consider both cases, okay? So let's say case number 1, your x is bigger than equals 5. So then square both sides. Why square both sides? Because that's what you need to show, right? So this is what you have over here. So you square both sides, your x square, sorry, that was rad5. Bigger than equals 5. Which is contradiction, right? Contradiction to what? This is contradiction to what the P, what the assumption, right? So what was your P statement or hypothesis? Was x is less than 5, but by this way, you got a contradiction. And then same thing, case number 2, let's say x is less than equals negative rad5. Squaring both sides. So then x squared is bigger than equals 5. We don't have any problem with this fact. This is okay. When you're rising both sides to the power of second, let's say on the left side of this x is less than negative rad5, you have maybe negative 4, right? But when you square negative 4 is 16. So it's going to be bigger than 5, right? Because your number, absolute value of your number is larger. So when you square it, still it's going to be bigger, okay? So whichever cases leads to your contradiction, so then you have to say Q was true. You have to say Q was true. Absolute value of x is less than 5. Can I add one? Do you guys have any question here? Any question for this one? Induction proof is something that we'll do it next time. So I'm going to add more examples here. Okay, so one of the examples that I have, it says prove. One of the examples says prove the product of two consecutive number integers only is even. Do you agree? Product of two consecutive integer is always even number. Do you agree with this statement? Product of two consecutive integer is going to be always even number. For example, 1 times 2, 2 times 3, 3 times 4, 4 times 5, 5 times 6. It's always even. Yes or no?
Yes.
It's always even. Why is always even?
Because you multiply it by an odd number and an even number.
So it seems you are always multiplying. One of them is even, one of them is odd. So it seems your argument is based on another statement. So you are just arguing based on knowing the product of an even and odd number is going to be always even. So your statement or your argument is based on something else. So I have to prove that one first, okay? So this kind of a statement that you are just trying to bring for proving or for helping to prove is called lemma. So the statement that you told me like that right now, product of an even number and odd number is always even, is another statement. It's not my statement. I have to show that one first, okay? So what I want to show first is product of an even number and an odd number is always even. So if I show once, I can use it forever. I don't have to show it always. So if I show it once that the product of one even, one odd is always even, so then I can use it as a lemma, as a tool, always for any other proofs, okay? So I'm going to show that one. So proof. I'll go with the direct proof. I'll go with the direct proof. So let n to be an arbitrary even number and m to be an arbitrary odd number. So n can be written as 2 times k for some integer k. M can be written as 2 times k sub 1 plus 1 for some k. I have to make it different because they are not the same necessarily, right? Thus, what is m times n? Is 2 times k times 2 times k sub 1 plus 1, which is a 2 out times something. For some k2 to be integer. Thus, m times n is even. So now it's clear for me forever, whenever I have one even, one odd, the product is going to be even. Fine by now? So now I can work on my main problem. Now you can work on your main problem. So you just want to show the product of two consecutive integers is even. So I have two cases. You can start with n to be even. You can start with the n to be odd. So what's a n plus 1? If I start with the n to be even, then n can be written as 2 times of k for some k. So then n plus 1 is 2k plus 1 n plus for some k. So n plus 1 is odd. Thus, product of these two consecutive integers is going to be 1 even times 1 odd, and it's going to be even by previous lemma. I'm going to write by lemma. And similarly, you can just write the second case, right? So if you started with the odd number, if you start with the odd number, then your next number is going to be even. If you add one more, so then the next number is going to be a 2k plus 2 or a 2k plus 1. Is even number. So then product of these two consecutive integers is going to be 1 odd first, 1 even next, equals even. Does it make sense? Can I move on to the next example? Any question here? So let's say here I have what do I have? If you have A equals just S sub 1, S sub 2 plus all the way to the S sub n, divide by n, which is the average of the numbers. This is the average of S sub 1, S sub 2 to the S sub n, prove there exists I such that Si is bigger than equals A. So you can think about if you have 2 or 3 midterms, if you have 3 midterms, your average is 60% out of 3 midterms. This is saying at least one of your midterms must be more than 60. If you have 3 midterms, the average of 3 midterms is 60%. So you have to have at least one of these midterms to be more than 60%. And I'm going to prove by contradiction. Okay, so this is going to be proved by contradiction. So what's the statement that you're supposed to contract? So what's the statement that you just say not Q? So what's the statement? What's the Q statement? So Q statement says there exists one I such that Si is bigger than equals A. So what's the Q naught? What's the Q naught?
For all of I,
For all of I,
specify is less than A.
okay. So this is, you assume, let's assume A to be this and Q naught. For all of I, Si is less than A. That's what you want to get the contradiction, okay? So let's see. If your S sub 1 is less than A, if your S sub 2 is less than A, if S sub n is less than A, if you just add both sides of the inequality, so S1 is to add to the Sn also is less than n times of A. So if you divide both sides by n, so then if you divide both sides by n, n is a positive number, right? So you can divide both sides by n. It doesn't change anything on your inequality. Is this contradiction with what the assumption is? The assumption says this number is exactly equal by A. The assumption says this number is exactly equals by A, but your God has to be less than A. So that's contradiction, right? These are not the same. This is contradiction, okay? Which is contradiction. By hypothesis of A to be S1, Sn divided by n. Therefore, I was wrong from the beginning that say the Q naught is true. There exists always one I such that Si is bigger than equal A. Question here? Any question here? Do you have any question? Okay. Prove that this 2m to the power of second plus 4n to the power of second minus 1 equals 2m plus n has no real solution. Has no real solution. What do you think? How do I prove this has no real solution? Any idea?
Move everything to one side. Set A equal to 0.
Okay. You're trying to actually solve it, but there are two main variables of m and n. There are two variables of m and n, and then you can't solve for two variables, right?
You have to kind of divide the variables. So you have two variables. You have to solve a polynomial for m and you have to solve a polynomial for n.
No, no, you are making really complicated. It's not that much. Any idea?
We, on the left side, that we directly prove that they're unequal by basically getting the left side to basically use properties to try to equal it to the left side. Because then if you have 2mn and you have mn minus, or I guess what you would be left with after factoring would be m plus n, and you would have 2mn minus 1.
Mhm.
And I guess what you would want to argue there is that 2mn minus 1 is greater
Mhm.
than 2m plus n. Or it's greater than 2 actually.
There's a contradiction saying that there is a real solution and
Almost right. It seems this inequality, I mean, sorry, this equation on the left side, you're having 2 times something minus 1, which is always odd number. On the right side, you have 2 times something, so it's always even. It's impossible one even number to be equal with one odd number. Yeah, that is true. So then I have to, yeah, that's exactly prove by contradiction. I said it's not that much complicated. Prove by contradiction. Let's assume there exists such a real solution, then 2m squared plus 4n squared minus 1 is an odd number. 2 times m plus 1, sorry, m plus n is an even number. then this is contradiction. Therefore, there is no real solution. Somebody says we can try some cases. Who says all right? The first one? The first idea, who was talking first? You said, yeah, proof by cases.
Oh.
Mm. So I have that kind of problem for you. So this is another example. It says prove 2m plus 5n squared equals 20 also has no solution. No solution in positive integers, sorry. Okay. That's just the idea of separate the cases. This is the idea of separate the cases because you are adding two positive numbers. That's the key part. Okay, if it's negative, it might be possible. Okay, so you are adding two positive numbers. You're adding two positive numbers. So you have 2m less than equals 20. You have 5n squared less than equals 20. Do you agree? If your addition is supposed to be 20, one of these has to be either equal 20, then the other part will be 0, or less than that, because they are positive numbers, okay? Because they are positive numbers. So that's just really interesting, but it makes it to the cases. So let's say m is less than equals 10. This is getting n has to be, what was it, 20, so less than equals 2, right? 20 divided by 5 is 4, so square root both sides is less than equals 2. So that in that case, we can really test, right? So you can just say, if I just test my m's to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, numbers less than 10, and then the other n to be either 1 or 2 positive integers. Okay, so that's why we have only 1 and 2 possibilities. So then you can just plug in back. You can just say, what is 2 times 1 plus 5 times 1? It's 7. What is 2 times 2 square? 2 times 2 plus, 5 times 1 square, so it's 9. So then you can try, there's no possibility. So you can try, I have numbers, sorry, I'm just copying the numbers because I have them. You plug in back and you see that is not possible. And even you don't have to really go all the way for the 2, because when you try the first one, it's already bigger than, when you try the first one, it's already bigger than 20, sorry. You don't need to continue. So that's just proof by cases. That's your idea. Yes, there are some of them that we can just show the possibilities by cases. Okay. Any question here? I'm going to leave one example for you and move to the quiz. Okay. This is for you. Prove for all real numbers if x to the power of second is irrational number, irrational, then X is irrational. Typically in the test, we ask you which way to prove, okay? So we have, make the job easier and we ask you to do in which way, okay? Eduardo? Christopher? I have Christopher P. Gregory? Alex? Jordan? Joseph? Christopher? Alexis? Tony? Nicholas? 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 Okay. Down. Oliver. Isana. Hi, Morris. Francisco. I'm going to pass the quiz and then take your time. Francisco, you're good. Leon? Anita, here. Okay. Nancy. One more. Kevin? Kevin? And Jerry? And Tommy? No, I'm sorry. Okay, we know not Monday is holiday, right? So we know Monday is holiday. I'll see you on Wednesday. Okay, so after doing your quiz, you're good to go. Yeah.